तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We acquainted ourselves with the concept of discrete time system function h of z in the last lecture. We defined this discrete time system function as the ratio of the z transform of the output discrete time signal to the z transform of the input discrete time signal with 0 initial conditions prior to the application of the input. The definition follows on close lines to the definition of the system function in the continuous time case. We also saw that if the difference equation pertaining the input and the output is of the form Fe operating on y of n is Ge operating on x of n, where Fe and Ge are operator functions, then we said the system function h of z can be obtained as g of z over f of z, where g and f are polynomials in z. We also observed that h of z is a z transform of the impulse response of the system, and we also said that for any given input xn whose z transform is xz, the output z transform is obtained as yz is hz times x of z. Now when you try to find out the time function corresponding to yz y of n, you make the partial fraction expansion of that, and you make the partial fraction expansion, certain terms come from the poles of h of z and certain terms come from the poles of x of z. The terms that are contributed by the poles of h of z will indicate the natural response or free response of the system. The terms that arise from the poles of x of z is the contribution which is due to the forcing function and which we call the forced part of the response. Now let us look at the natural response in some detail. So natural response or free response arises from poles of h of z. So in the natural response, if the set pi are poles of h of z and are all distinct, that is no pole is repeated, then the natural response is of the form ai pi raised to the power of n summed on I. It's something which we already know from our partial fraction expansion. Now if a particular pole is repeated, what happens? If a pole pi of order k exists, that means a particular pole is repeated k times, that means z minus pi raised to the power of k, z minus pi raised to the power of k is a factor of f of z, then the natural response will be the form due to this will be of the form a naught plus a1n plus a2n squared right up to nk minus 1 nk minus 1 multiplied by pi raised to the power of n. That will be the natural form of the response. So, to look at these natural response forms, let us look at these charts here, which will give you some idea. Now, depending on the location of the poles within the unit circle, you have different types of responses. Suppose there is a pole at z equals 1, that means right at the one end, at the rightmost corner of the rightmost end of this circle, z equals 1, then naturally the response will be a unit step. On the other hand, suppose there is a pole at z equals a, where a is less than 1, then that means it will be a to the power of n, it is a decaying type of response that you get. On the other hand, if there is a pole which is on the real axis at a distance greater than 1 from the origin, that means this is a rising response, so it goes up like this. On the other hand, there is suppose there is a pole at minus 1, and that indicates a response which is plus 1 and minus 1 alternately. It is minus 1 raised to the power of n, so it becomes alternately plus 1 and minus 1. On the other hand, if there is a pole at say minus a, where a magnitude is less than 1, then minus a raised to the power of n, again it indicates a decaying response with alternate samples being positive and negative. Suppose there is a pole at on the negative real axis at a distance larger than 1 from the origin, then again it is an increasing response which is alternately positive and negative. So, it is clear from the point of view of stability that all the poles must be within the unit circle, as we have seen here. In this case, the poles here, here and on the unit circle indicate stable response. Let us see what happens when we have complex conjugate poles. Suppose we have complex conjugate poles. Suppose there are complex conjugate poles on the unit circle itself, then that indicates a steady response, a sinusoid, either a cosine or a sinusoid. We can put sin omega, n omega t, n omega plus theta as a general form. On the other hand, if the poles are situated, complex conjugate poles at a distance less than 1 from the origin, then it indicates a decaying oscillations, amplitude decaying, and that again indicates a stable response. If the complex conjugate poles are at a distance s from the origin, where s is larger than 1, it again indicates oscillatory behavior, but the amplitude of the oscillations goes on increasing. This clearly is an unstable behavior, and that arises because the poles are at a distance larger than 1 from the origin. Let us take the third chart. Now, here we have, let us take a case where there are double poles. There are two poles at the origin at z equals 1, then that will be the form, the response will be a plus bn. It increases, the response increases with n, and therefore this is clearly an unstable situation. And on the other hand, if you have complex conjugate poles, a pair of complex conjugate poles which are of order 2, then again it is a sinusoid with increasing amplitude. It will be of the form a plus bn sin n omega plus theta. So, clearly for stable behavior we require that the poles be within the unit circle. It does not matter of any order, as long as they are within the unit circle, the poles may be of any multiplicity whatsoever, and ultimately the response will decay with time. But on the other hand, if there are poles on the unit circle itself at a distance 1 from the origin, then those poles must be simple. That is the sum and substance of the restrictions on the pole locations for a stable discrete time system. You recall that in the case of continuous time system, we said for a stable system all the poles must be in the left half of the S plane, and if they are in the imaginary axis they must be simple. In a similar way here, for a stable system we demand that the poles must be within the unit circle. If they are on the unit circle itself, they must be simple. Now, let us also look at the forced response characteristics. We have seen that if the input xn is wn, the forced response is the form h of w evaluated at w times wn. This can be easily worked out using the partial fraction expansion, and that means the x of z will be z upon z minus w and find out the residue corresponding to that pole, and you can work this out. It can easily be shown that this is so. This also can be seen from the point of view that is a characteristic signal, and the output is also a characteristic signal for a discrete time system, and the coefficient will be h of omega. W can be any particular value. It can be a complex constant, it can be complex also, it need not be real. So suppose we take E j n omega. That means W is now identified, this is W. W is identified as e to the power of j omega. So the force response will be h e to the power of h of e to the power of j omega times e to the power of j n omega. Now let us take cos n omega, which is the real part of e to the power of j n omega. So the response due to this, the forced response due to this, which in this case happens to be the steady state response, because this is a steady state input. The steady state response due to that, assuming that all the transients, all the natural response is a decaying type, the steady state response to that will be obtained by taking the real part of this, because you are taking the input as the real part of this, the output will be the real part of this. So the real part of this of h e to the power of j, h of e to the power of j omega e to the power of j n omega, which can be written as h e to the power of j omega magnitude, because this may have a magnitude and an angle, so h e to the power of j omega magnitude times cos n omega plus theta omega, where the h e to the power of j omega, suppose I write h e to the power of j omega as h e to the power of j omega magnitude and with an angle theta omega. So the angle associated with h e to the power of j omega, the theta omega is the additional angle in the cosine function, and the magnitude is modified by this. Similarly, you can write sin n omega, you can show that the output will be h e j omega magnitude sin n omega plus theta omega. So when you are driving this with a sinusoidal input sequence, then the output is also a sinusoid under steady state conditions, assuming the transients have decayed down with time and we are dealing with stable systems. The input sequence is modified in amplitude by this factor, and it is modified in phase by this factor. So clearly h e to the power of j omega has the same role to play in the frequency, deciding the frequency response, as what you had in h of j omega in the continuous time system. So this is called the frequency response function. So in the discrete time case, the frequency response function is obtained from the system function h of z by substituting e to the power of j omega for z. In the continuous time case, you substitute j omega for s. Here you substitute e to the power of j omega for z. So this defines the magnitude and the phase, both are functions of omega, the particular frequency of the input sinusoid. Now to obtain h e to the power of j omega, you can, once you know the rational function corresponding to h of z, you can certainly substitute e to the power of j omega for z and evaluate both the magnitude and phase of the frequency response function. Alternately, you can say, suppose h of z is of the form m z minus zi product. So the numerator is factored, and these are the various 0 locations, and the denominator have poles, and these are the various pole locations p1, p2, p3, and so on and so forth. So when you want to evaluate h of z, when z takes the value e to the power of j omega, h as a function of e to the power of j omega will now be m times the product of e to the power of j omega minus zi divided by the product e to the power of j omega minus pi. So all this means is you are evaluating h of z at a point e to the power of j omega, e to the power of j omega is clearly a point on the unit circle. So you take a point on the unit circle corresponding to the omega that you are considering. The distance from that point from the each 0, each term represents the directed line from Zi to the particular point under consideration. So you take the product of all those complex factors, divide by similar products of the lines, complex numbers representing the line joining pi to e to the power of j omega, multiply by the scale factor, that will give you the frequency response. To put this in other words, let us look at this diagram where we have the poles and 0 locations of h of z are marked here. Zeros are marked by circles and the poles are marked by crosses. Suppose this is the point at which you want to consider the frequency response, that means this angle is omega, e to the power of j omega is this point. So the line from a particular 0 to this will have, let us say this is Zi, the location of this is Zi, and let us say the line has a length mi and an angle alpha I. Similarly, you consider for each pole, suppose this is the pole pi here. So you draw a line here, and this let us say this is capital Mi, the length, and the angle beta I. You repeat this at the point under consideration. You consider such line segments from all the poles and zeros. You can now say that the frequency response function evaluated at that point equals the constant multiplying factor m is there, which we had here, that is a constant multiplying factor, times the product of all these line segments going from the origin. Therefore you have product of all these small mi's divided by the product of all these capital mi's, those are the poles. In addition, this will have an angle which is summation of alpha I minus summation on beta I. So this is the angle associated with the frequency response function, and this is the magnitude of the frequency response function. So one can visualize the frequency response of a particular discrete time system by looking at the poles and zeros, and as you move along this unit circle you can pick up the nature of the variation of the frequency response for different frequencies. Clearly this is point corresponding to omega equals 0, and this is equal to omega equals pi by 2, and this is equal to omega equals pi. Now when you are talking about a sinusoidal signal sin n omega and cos n omega, we are assuming here that the spacing between different samples is 1 second. Actually we should have written sin n omega t in a general case, where if this is the time axis, we are talking about 0, t, 2t, 3t, etc. So in this case you would have to write sin n omega t, because the samples are displaced from one another by an angle, by an amount of t seconds. But here we are talking about a normalized case where capital T is 1 second, and therefore the omega turns out to be the angle itself. So omega t you should have had. Actually what we are plotting, the angle is omega t, but t being 1 second, omega itself is measured in terms of radians. It's a normalized frequency variable. So omega in this case can be called normalized frequency variables, normalized radian frequency. I will discuss in a minute what happens if you do not have this normalization, but we will postpone that for the time being. We will assume that t is capital T is 1 second. What we observe here therefore is, as you change the frequency, you can calculate the frequency response. You can go up to pi, 2 pi and so on. Suppose you come back to 2 pi and start all over again, you must get the same frequency response, because as you move along this unit circle, complete one circle and come back to the same point, you must have the same frequency response. That means as omega increments by 2 pi radians, whatever frequency response we had in the original value will continue to be the same at the new value, which means in other words that the frequency response function of a discrete time system is periodic in character. So let me illustrate that a little more in greater detail. So, the frequency response function, suppose you want to plot the magnitude of the frequency response function with as a function of omega, then as you can see that it must be periodic in character, because as you move around the unit circle you come back to the same values after every rotation through 2 pi radians. So, this is periodic in character, and that is something which is a fact of life as far as discrete time signals systems are concerned. Now, I mentioned that we have taken here the normalized frequency, that means the sampling period is equal to 1 second. Let us look at a general case where discrete time systems are commonly used. A digital filter gives a particular example of a discrete time system. In a digital filter, what is done is a given analog signal, continuous time signal x of t is digitized, is discretized, you generate from this through a sample and hold circuitry and analog to digital converter and whatever it is as x and t. That means this is a discrete time signal with sampling space between 2 adjacent samples being t seconds. So, this is called the sampling period t, and we also indicate omega s as the sampling frequency in radians per second or in hertz f of s 1 over t. This is also called sampling frequency. This is in radians per second, this is in hertz. Now, this input sequence is given to a digital system, which is we call the digital filter in this context, and we get an output sample y and t, and the system function corresponding to this discrete time system is h of z, and therefore the frequency response for this now will be h e to the power of j omega t instead of e to the power of j omega, because we are now taking a general sampling period t instead of where we want to evaluate this frequency response of this system function, you must substitute e to the power of j omega t rather than e to the power of j omega. And once you have the output sequence, then you put through some filters to remove the high frequency components and so on. This is what is called analog reconstructor. You can recover back your y of t. So, given an analog input signal, you get an analog output signal, but in between you convert this into a discrete time signal, and the frequency response of the system is characterized by h e to the power of j omega t. So, you design your filters so that this h e to the power of j omega t has the desired variation with reference to the frequency. Now, if h e to the power of j omega t is the frequency response, then our unit circle now, earlier in terms of the normalized variable we put 0, pi, pi by 2 and minus pi by 2, minus pi and so on and so forth. But in terms of the actual frequency now, you can write this as this is equal to omega s, this is minus omega s, this will be omega s, I am sorry, this is omega s by 2, this must be omega s by 2. I will write here pi here, I will write here my omega s upon 2, this is omega s upon 4, this is minus omega s upon 4 and so on and so forth, and this is of course 0. So, we graduate this unit circle if you want to do it in terms of frequency, actual frequency omega. So, when we want to evaluate the frequency response at omega s upon 4, this is the point which you should consider. In the normalized case it becomes pi by 2. So, the connecting link between that is omega t is now the angle that you have to use instead of simply omega. So, at any particular frequency if you want what is the angle, this must be omega t. At that point you must evaluate the frequency response, which means that in terms of the frequency response characteristics here, in terms of actual frequencies, this will be 0, this will be omega s upon 2, this will be minus omega s upon 2. We can say denormalized frequency. So, if you do not normalize it and consider this omega as such in the raw form, general t, then this would be how it is. So, the frequency response of a digital filter or any discrete time system in general is periodic in character, and that period, this omega s, depends upon the sampling frequency. That means, if the period sampling period is t, 2 pi by t is the sampling frequency omega s, and this is the base period. So this period, whatever occurs in one period repeats itself identically as we go along. Just as an illustration of how we can obtain the frequency response from the pole 0 plot, let us take a particular discrete time system function which has got a 0 at an angle pi by 3 and minus pi by 3, a pair of zeros, complex conjugate zeros, and poles which are very close to them on the same line. So the system function, let us say, is this is Z1, this is Z2, this is P1, this is P2. That means system function is Z minus Z1 times Z minus Z2 divided by Z minus P1 times Z minus P2. That we have taken a constant multiplying factor as 1. So what will be the frequency response of this? Suppose we ask, then the answer will be, so h e to the power of j omega magnitude is what we are plotting. Now at this point, that is the DC value, when omega equals 0, the distance between at that point from Z1 and P1 are nearly the same because it is very close to this. Similarly P2 and Z2 are very close. So as a matter of fact, as you move along this line, at almost most of the points, the distance between the roving point and the distance of the roving point from P1 and Z1 will be the same, and the distance of the roving point from P2 and Z2 will be nearly the same. However, as you approach this point Z1, then the distance becomes 0. So clearly if you are sitting here, the length of the line segment from the roving point to Z1 is going to be 0. That means the numerator is going to fall down to 0. So if you plot the frequency response for this, you will have more or less equal to 1, and suddenly it jumps back to 0. So it will be the same thing in the reverse direction. So as a function of omega, it will be like this, and this is DC, and this point corresponds to, suppose we call this 60 degree, pi by 3 I have mentioned already, therefore this is pi by 3, and when this is pi and this is minus pi, the same thing repeats itself again and again. So this is what is maybe called a notch filter. That means the output is reduced to 0 at a single frequency while trying to maintain the output at the same level as the input for the rest of the frequency. So if this is 1, almost it is 1 everywhere except at this particular frequency. This is what is maybe called the notch filter, and in terms of the sampling frequency, this will be omega s by 2, this will be omega s upon 6. So such filters are designed to blank out some particular undesired frequencies in a given system. This is what may be called the notch filter. So what we have discussed so far in the discrete time systems, the treatment of discrete time systems, we have started with the concept of discrete time signals. These are signals which are defined, specified at distinct points of the independent variable. The independent variable can be the position, a length, or time. We take time to be the commonly as the common independent variable. Commonly we take that to be the independent variable. That is why we call this discrete time signals. And systems which operate on discrete time signals, which take an input sequence of these sample values and then produce a corresponding output, are called discrete time systems. And these systems of the various kinds of discrete time systems that are possible, we confine our attention to the linear time invariant case, where the systems are described by linear difference equations with constant coefficients. And then we saw how to analyze these systems based on the difference equation approach. We looked at briefly at the classical method of solution of difference equations, and then afterwards we studied the operational methods, the transform methods, but applicable to a discrete time system. This particular transform is called the Z transform, which is the counterpart of Laplace transform in the continuous time case. We saw the various properties of Z transforms, and we saw how the Z transform enables us to convert a difference equation into a purely algebraic equation, and then we worked out a few examples showing the efficacy of the Z transform method in the solution of the transients associated with the discrete time system. We also looked at the discrete time system function h of z, which is the counterpart of the h of s, the continuous time system function. All the properties are more or less the same. H of z is the Z transform of the impulse response, and we saw that the poles of h of z will specify will indicate the character of the natural response of the system, and for stability these poles must be within the unit circle. If they are on the unit circle, those poles must be simple of unit multiplicity. We also saw that H evaluated at a point in the imaginary axis, at a point in the unit circle, will specify the frequency response. There is a correspondence between the point and the unit circle and the particular frequency at which you want to find out the frequency response. We saw the various issues relating to that. Importantly, we noticed that the frequency response of a discrete time system is periodic in character. There is a base period which is equal to 2 pi by the sampling time t, 2 pi by t or omega s, the sampling frequency, and whatever is happening within that base period gets repeated for subsequent intervals. So any filtering you want to do, you must make sure that you do not have components outside that, or if you have any components outside that, you must somehow cope up with the periodic character of the frequency response function. So usually what is done is you would confine all the filtering that you need to do within the base band of that, and you see that you do not have to contend with components outside that base band. And in discrete signal processing, discrete time signal, DSP, digital signal processing, these techniques play a vital role, the Z transform methods and the frequency response and so on. What we have not done in this particular course of lectures, particular set of lectures, is we did not discuss the concepts similar to Fourier series and Fourier transforms in the continuous time case. Here also we have discrete Fourier series and discrete Fourier transforms. These follow an analogous lines as the continuous time systems, and we can think of discrete Fourier transform as a special case of the Z transform when Z is e to the power of j omega, but that is something which is outside the scope of our lectures, so we did not discuss that in this particular set of lectures. The importance of discrete time systems is growing day by day, particularly with the digital signal processing, and these techniques that we have discussed here will enable you to study the digital signal processing and allied topics with this will give you a good foundation for studying these topics, which are becoming more and more important today with the computer hardware available and digital signal processing hardware available to you. And these are becoming very important not only in communication but also in control and instrumentation. So what you have studied here will be quite useful for you to take up advanced topics in DSP and similar related subjects. At this time now we will put an end to our discussion of, we will stop our lectures on discrete time systems at this point. I will give you an exercise for you to work out on the topics that we have studied under discrete time systems. First problem in this exercise, I am giving you certain difference equations. State if the discrete time systems governed by the following difference equations are causal, linear and time invariant. So examine each of these difference equations, state if they are causal, if they are linear, if they are time invariant. One or these other attributes may be absent. First one, yn cos n omega xn. The yn is always the output and xn is the input. B, yn equals 3 times x of n plus 2. C, yn is 6 times the magnitude of the signal x n minus 3. So take these three and for each of these examine if they satisfy the property of causality, linearity and time invariance. This is the first example. The second question is, sketch the following discrete time functions. So, we give you a number of discrete time functions symbolic fashion, you try to sketch the samples, the sequence of samples showing the waveform of the signals. A, delta n plus 1, B, u of minus n plus 1, C, n times u of n minus 2. It is understood un is the unit step function, so you must find what un minus 2 is. D, n minus 2 multiplied by un. E, n minus 2 multiplied by u of n minus 2. You must see the difference between C, D and E. F, un multiplied by another discrete time signal u of 3 minus n. G, un minus u of n minus 3, and H, 0.6 raised to the power of minus the magnitude of n. So, for positive n it is minus n, for negative n it is of course minus of magnitude of the negative n. That means it will be symmetrical in both directions. 0.6 raised to the power of minus the magnitude of n. So, you sketch the discrete time functions pertaining to these various functions given in symbolic form in this fashion. 3a, this is a discrete time system given as an assembly of delay units, coefficient multipliers and adders. Find the difference equation corresponding to the system given, difference equation joining the output yn with the input xn. So, the difference equation in terms of yn and xn. Yn is the output and xn is the input. So, xn is fed to a delay unit, 1 unit delay, fed to another delay unit, and this is given to a coefficient multiplier with a coefficient half, multiplication factor half. This is given to as one input to a adder. The output of the adder goes to yn, that is the output. The output is delayed by 1 unit in this, another 1 unit in this, and the two delayed versions are multiplied by coefficient 1 and minus half respectively, and the outputs of these coefficient multipliers are given as additional inputs to the adder here. So, the sum of these 3 inputs is your yn. So, we find the difference equation corresponding to this system joining yn and xn. Find another realization of the same difference equation using fewer delay elements. You will observe that this is going to be a second order difference equation. So, in principle a second order difference equation can be realized with 2 delay units. We have used 4 units here. So, you try to find out another discrete time system which realizes the same difference equation, but using fewer delay elements. Fourth question, working in time domain and using step by step procedure, find the impulse response of the systems described by the following equations. Take initial conditions prior to application of impulse to be 0. So, you take the output yn to be 0 for n less than 0. The two equations are yn minus 0.8 yn minus 1 equals xn. According to usual convention, xn is the input and yn is the output. You have to take xn to be the impulse in this case. Work out to the iterative procedure and find out the solution for yn. The second equation is yn plus 2 plus 3 yn plus 1 plus 2 yn equals xn. So, this is the second order difference equation. So, for these two systems, two difference equations, you take xn to be the impulse and find out the yn as a sequence of samples taking yn to be 0 for value n less than 0. Second example, next question, example number 5, question number 5. Use convolution summation to find the response of the systems in question 4, these two earlier difference equations, but this time to an input 0.5 un, taking initial conditions once again to be 0 for n less than 0. So, for the same two equations, taking the input now to be 0.5 un and use the convolution summation, because you know the impulse response already, use the impulse response and then the new forcing function 0.5 un, use the convolution principle to find out the new response for the two systems. Sixth question is, find the complete response of a system having the difference equation yn minus 1.6 yn minus 1 plus 0.64 yn minus 2 equals xn. This is once again a second order difference equation. For an input xn, which is the step un, we are given the two initial conditions, y minus 1 equals 1, y minus 2 equals 0. Now solve this using the classical method of solution of difference equations. So you find out from the auxiliary equation, find the complementary solution and find the particular solution for the given input function un. Use the classical approach to find out the solution for this using the two initial conditions. Seventh question is, you are given a sequence of discrete time functions, find out the Z transforms a 2 plus 3 e to the power of minus 2n all multiplying un, 1 plus minus 1 raised to the power of n e minus n un. That means alternatively this will be plus 1 and minus 1. When this is minus 1, this whole thing becomes 0. When this is plus 1, this becomes 2. So you get alternate samples. 1 plus minus 1 raised to the power of n, whole thing multiplying e to the power of minus n un. C n squared un, d n e to the power of minus 4n un, e n times un minus un minus 5. That means this is a kind of gate function. That means un minus 5 means that you have values only within the from n equals 0 to n equals 4, as you can see, that multiplied by n, plus n minus 5 times un minus 5 times un minus 10. This again a set of samples, plus n minus 10 multiplying un minus 10 minus un minus 15, and this pattern repeats itself endlessly. So I put dotted lines. So it will go on like this. Next is n minus 15 times un minus 15 minus un minus 20, and so on and so forth. So find out the Z transforms of all these discrete time signals. I will give a few more I will write them down afterwards. This problem will continue in the next presentation. This is a continuation of problem 7 where you are asked to find Z transforms. Next part is summation from k equals 0 to n of un minus k uk e to the power of minus k alpha. You recognize this to be in the form of convolution summation, so you should use the appropriate properties. G w raised to the power of n alpha multiplied by un minus u of n minus capital N. So this is a pulse function multiplied by w to the power of n alpha. Find out the Z transform of this. The next question is, you are given a series of Z transforms. You are asked to find out the discrete time functions which have this Z transform. That means you have to find out the inverse Z transform. A 5 upon Z minus e to the power of minus t. B Z squared upon Z squared plus 1. C 2Z upon Z squared minus 2Z plus 1. D 6Z squared upon 2Z squared plus 2Z plus 1. I will read this again. 6Z squared divided by 2Z squared plus 2Z plus 1. So you have to find out the inverse Z transforms of these four functions. Question number 9, solve the difference equation question 6 using the Z transform method. Earlier in question 6 you are given a difference equation and you are asked to solve that by the classical method of solution of difference equations. Now you repeat the solution, this time using the Z transform method, and compare the answers. Both must be the same. This again pertains to the same difference equation as given in question number 6. The last question in this exercise, you are given a discrete time system modeled as in this diagram. You have an xn fed as one input to an adder. These are the other two inputs, and that goes out to another adder with an additional input that forms the yn, the output sample, and whatever signal is coming here is delayed by 1 unit in this delay unit and another 1 unit in this delay unit. The two delayed versions are multiplied by coefficient multipliers, using coefficient multipliers by coefficients half and minus 1/4, and the outputs are fed to this adder, and the signal at this point is fed to this adder. These two together will contribute to yn. So using this model of a discrete time system, find the difference equation pertaining to the output yn and how it is related to xn. So relating yn and xn, find the difference equation from this circuit representation. Find the system function for the same system h of z, that is the z transform of yn, the ratio of z transform of yn to the z transform of xn with 0 initial condition, that is h of z. Using the z transform, find the impulse response of the system and find the step response of the system. Whenever we normally talk about impulse response and step response, we assume 0 initial conditions prior to the application of these two inputs. So that is assumed. We are not stating that specifically. Find the impulse response and z step response of the same system using the z transform methods. And in the solution here, identify the natural and forced response components in C. For each of the solutions, find out what is the natural component of the solution or the free component of the solution and what is the forced response component of the solution. E, find the steady state responses to the following inputs of the same system: sin n pi upon 4 to cos n omega t, where omega is given as 500 pi radians per second and t is 1 millisecond. So cos n omega t, omega is 500 pi radians per second and capital T is 1 millisecond. So for these two sinusoidal inputs, find out the steady state output, that means it will also be a sinusoid, and because the natural response is expected to decay with time, and using the frequency response function, find out the output corresponding to the two inputs.
Thank you.